In this video, we're going to talk a little bit about heat of fusion and heat of vaporization. So I'm just going to draw a quick heating curve up here. Okay, and we had these two plateaus. One between solids and liquids, and one between liquid and gas. The plateau between solid and liquid is called, or that amount of energy is called the heat of fusion. So right, if we added up how much energy were added right here, that would be the heat of fusion. Likewise, for the liquid and gas, if we added up the energy, it would be called the heat of vaporization. My picture is pretty bad, but I did try to make the heat of vaporization larger than the heat of fusion. So let's think about what's happening here. And remember that in these stages, right, in the graph, energy is being added, and it's being added to potential energy and not kinetic energy. That's why they're flat. And the temperature is not increasing as we add energy. And kind of as you go through those plateaus, more and more of the atoms or molecules are getting sufficient energy to either break out of the crystalline structure or break away from the other molecules to either become a liquid or a gas. And this is when the very big changes in their properties happens, right? Going from a liquid to a gas, your volume, like the volume might expand by like over 1,000 times. You know, these are non-trivial differences. Liquids can flow by each other; they don't have a rigid shape, etc., etc. And so some important stuff is happening in these two plateaus. So I'm going to introduce a new kind of graph that I just like to use. And I guess I'll have, let's see, I'll have these kind of blank bars that represent kinetic energy and these dashed ones to represent potential energy. And this will represent negative 20 degrees Celsius ice. Right, and then we have energy here on the y-axis. And you see the potential energy is below the x-axis, implying that it's negative. Now when we add extra energy to this, so say we're going to take it from the starting point to ice's melting point, which is 0 degrees Celsius, its kinetic energy would definitely increase by a little bit. And its potential energy might increase a little bit, but not very much. So this would be 0 degrees Celsius ice. And you can see that the kinetic energy got bigger and the potential energy may have gone up a little bit. Right, and going up means less negative. And if I were going to draw 0 degrees Celsius water now so they have the same temperature, liquid water that is. They have the same temperatures, so they'll have the same amount of kinetic energy. But the liquid will have significantly less potential energy. Right? And you see that there's this gap here where we added some energy to that. So if we're going to give you kind of like example numbers, if it were negative 10 for the ice, maybe it's negative 8 now for the liquid, which means that there used to be kind of these 2 joules of negative, there used to be like negative 2 units of potential energy down there that aren't there anymore. And to do that means we added 2 units of energy to go from negative 10 to 8, negative 10 to negative 8. And if we went from 0 degrees Celsius liquid to 100 degrees Celsius liquid, again you'll see a kinetic energy increase. And the potential energy might increase a little bit, but not too much. And then the last stage would be to make this into 100 degrees Celsius gas. And again, we'll have the same temperature. So the same kinetic energy, but now gas has no potential energy. We're assuming that it has kind of 0 potential energy. Right? So there's this whole section here of energy that you had to put in to get to this level. So if this is at 0, we would have had to add 8 units of energy to the liquid to get it to the gas, and that all goes into potential energy. And the one thing just to be careful about here is remembering that we have to add energy to the negative potential energy to get it to increase, get closer to 0.